Hi everyone. I know you missed me, so I am back, sooner this time. But this time, I am back with a technique, which will totally not help you any better than you already know about avoiding problems, especially people's. But it'll definitely help you make this cool Pac-Man animation, which is totally procedural. Notice how he's running towards the target while avoiding these obstacles, using the shortest possible path, and also changing the path as the target position updates. Also, I'll be explaining how this find shortest path node sort of actually works under the hood. Spoilers, Dijkstra's algorithm. Let's begin. I'll start by a short overview of this Pac-Man model and how I created this procedural level generator. So for the Pac-Man model, I am simply preparing these two models with a Boolean operation, which I can switch using this simple sign expression so that it gives the classic illusion of mouth opening and closing. I can now instance points over the geometry on a random orientation to give it a voxelized representation. Ah, yes. The classic pixel look. Now to the level generator. Here, I used a grid with square division, which is very important, and used the width of the very first primitive, which is equal throughout, to generate an L-shaped primitive wall, while making sure that the inner conjunction point of the shape is at the very origin, as we're going to instance and rotate from that point only. Now we can select any random points, making sure the point belongs to only the grid we made earlier, as the L primitive is made of the exact same area as the squares in the grid we made earlier. If we want, we can use simple grouping from object bounds to art direct the places where we don't want our points to be scattered or obstruct. Now, once we're happy with the scattering, we will use a simple algorithm, utilizing quaternions, to rotate the normals. Now, once we're happy with the scattering, we will use a simple algorithm, utilizing quaternions, to rotate the normals of our each scattered points randomly, while making sure that the rotation only happens at the cycle of 90 degrees, which is 1.5708 radians. Now that we have the normal calculated, we can instance our L primitive, so that it's rotated randomly at different quadrants. Now that we have both the base and the obstructions, we can use simple extrusion and coloring for the final procedural model, and there you have it. A Pac-Man model and a procedurally generated level base. Awesome! You made it to the best part. Now we're going to the actual bread and butter of the video, which is to instruct a point to roam across to a target position taking the shortest possible path, and all that, while avoiding these level obstructions. Let's jump right in, and first understand how are we going to generate the shortest route to a destination. It's simple. We're going to use Google Maps. No, literally. Well, sort of. At least the algorithm, admittedly, the poor man version of it. So the algorithm that we're going to create in Vex, with a little spin of our own, is inspired by this algorithm, which is known as Dijkstra's algorithm, which, in short, basically states that, in order to reach a target point, a point should be aware of all the possible paths towards the direction of the target, and must add the knowledge of the previous position at each iteration or step, in order to add up and determine the shortest route. So now that we understand this, we'll make one for ourselves using Vex. So here I have a grid with some divisions. Let's choose a single start point and a single end point. Also, to prove my point and make it a bit interesting, I'll delete some primitives to exclude from the path. I use these expressions to set a start and an end groups, stored as a point attribute. Now, we're going to write the code for a single iteration first, to check if we're getting the desired data. So I'll simply use a for loop network and place my point wrangle inside it. By the way, I am giving away this entire file for free in case you wanted to check it out, as I'll not do an in-depth explanation of each and every step, so I'd really appreciate if you could follow me on these platforms, if you haven't already, also, to know where you can download the file. Back to the wrangle. So we'll start by creating some necessary attributes that we need to initialize in order to store the information about the current position and the point number of the start point and end point. We'll now create an empty array to store the found points on each iteration, and immediately store the start point into the array. Now, we want to know which primitive is the start point originating from. In case the primitive point is common for more than one primitive, we can use the last primitive from the stored list, and then simply use a primPoint attribute to store all the 4 points on the stored primitive. Now we can simply check which of the 4 stored points is the closest to the position of the endpoint we stored earlier, and also what is the point number of the closest point. Now that we know that, we can literally forget about the previous start point and make the newly found point from the array as the actual start point for the next iteration, and also append the found point into the array we made earlier. So now, at each iteration we have a new start point which is the part of the same primitive as the previous start point, and also, since the endpoint is the same, the next start point is repeating the steps by the number of iteration we call it for, while also appending the point numbers at each iteration to the edge array which is storing the point we will define our path from. How do we do that without manually deciding the iterations? Well, we can use a while loop, and cleverly say, as soon as the condition, which is the start point literally being the end point, we will break out from the loop. And ta-da! We have an automatically breaking iterative loop, but we're not done yet. Remember the empty array we made earlier where we stored the first starting point into? Now that array is filled with a list of point numbers which were the previous start points, which we can simply now connect with an addPrim function. And congratulations, you made a poor man's Google map yourself right into Houdini. Also, you sort of recreated what this node, find shortest path, does in the background. So now that we understood that, we can move on to the application. I'll start by creating 2 points to determine the start and the end position, whose position I'll transfer back to the base grid using the nearPoint function. Also, we'll subdivide the grid to make enough primitives for path generation and propagation. Once we have that, we'll convert the obstacle mesh into VDB and use the volume to define a group which will act like obstacles. We can now make some attributes, let's say, heat, and blur it with massive iterations, which will give us a gradient between the start and the end position. We will also make sure that we're excluding the obstacle mesh from the blur, so we can get the gradient value starting from the obstacle area as well. Simultaneously, we will use the find short path node to calculate the shortest path between the start and end position. I am using the default node, but you may experiment like we did earlier. Both works fine. Now we can use the tangent of the path as the gradient vector, which we'll also calculate with the measure SOP by using the heat as the source attribute. Now we can transfer the gradient vector from the path and blend it into the calculated gradient from the grid. And if we view a normalized vector visualization, we can see we have these vectors directing the path we need for the source position to get to the end position. Now using a SOP solver, and these simple expressions which are telling the source point to query the gradient vector from the nearest grid point, and add it to its current position, we now have a fully automated point which is traveling to the destination while avoiding the obstacle. Now we can use a point velocity SOP to calculate orientation, and instance the Pac-Man model over the animated point. By the way, we can also animate the target point, and cache the animation out. So there you go. We made a fun little game while learning about some very interesting computer graphics algorithms, like always. Hope you enjoy the video. Don't forget to check out my Instagram where I have posted the link to this file in the bio. See you next time, with more fun Vex experiments. Till then I'll be avoiding you. Take care.